Today I'm going to work some problems using conservation of energy. And I thought what we would do is we'd actually look at the same problems we used in the previous examples using the work energy theorem and show how we can make the problems even easier using potential energy and conservation of energy. All right, so the first problem we looked at was with a non-conservative force, where we had a crate of oranges sliding and coming to a stop because of friction. Well, this problem we cannot simplify using conservation of energy because friction is not a conservative force. So we can't use our conservation of energy. So what we did last time is probably as good as it gets. So let's move on to the next problem, accelerated by its spring. So a spring with a spring constant of 283 newtons per meter and a length of 10 centimeters is sitting on the floor. Then it is compressed to a length of 7 centimeters. A 200-gram mass is placed on the spring, and then the spring is released, launching the mass straight up. How high above the floor will it go? Well, we have a similar diagram to what we had before. We have the mass sitting on top of a spring, which is compressed to a length LC. The initial velocity is 0. The spring has a spring constant K. The mass has a mass M. There are two forces acting on it initially. There's the force of the Earth on the mass, gravity, pulling it down. And then the force of the spring on the mass is pushing it upwards. A little while later, the mass has been accelerated upward. The spring reaches its uncompressed length, and the mass leaves the spring and continues to go up further, reaching a final height, h. At this point, once it leaves the spring, there's only one force acting on the mass, and that is the force of gravity. Now, again, our objective is to find h, the highest point, how high up the mass will go. Our givens are the same as they were before. We're given the spring constant, the compressed length, the relaxed length of the spring, and the mass. And of course, we're going to assume that we know that gravity is 9.81 meters per second squared. Okay, so last time we used the force energy equation, and we had to do a bunch of integrals and things, and it was kind of annoying. It was better than trying to do it with F equals ma, but we're going to make things even better. We're not going to try that approach. We're going to use a simpler approach. We're going to use conservation of energy. So our basic equations are going to be the initial kinetic energy plus the initial potential energy is equal to the final kinetic energy plus the final potential energy. And of course, kinetic energy is just 1/2 mv squared. The potential energy of a spring is 1/2 kx squared. And the potential energy due to gravity is mgh. So our solution looks like this. The initial kinetic energy is 0. It's not moving. The potential energy due to the spring is just 1/2 times how much the spring is compressed squared. The amount it's compressed is its relaxed length minus its compressed length. And then the initial potential energy due to gravity is just mg L sub c. Once it reaches its maximum height, the kinetic energy again is 0 because it comes to a stop at the top. The spring potential energy is 0 as well because the spring is the mass left it and it was at its relaxed length. But we still have potential energy due to gravity, which is mgh. And so we just take this equation and divide both sides by mg, and we have h. It was that simple. Remember, it took us a bunch of work before to get our answer. Using conservation of energy, it was that simple, and we have our height. And again, we can plug our numbers in just like we did in the previous set of examples, and we get 0.135 meters or 13.5 centimeters. The units work out just like they did before. Gauge and guesstimate, once again, 13.5 centimeters seems reasonable. It's not crazy. And then, of course, we can do the same kinds of things with limits, looking in, how would we expect changing g or m or k to change the height, and so forth. So we got the same answer we did last time, but it was a lot easier. Now let's look at the swing problem. So as you recall, last time we said we wanted to find the acceleration you feel at the bottom of a swing. All right? And so we drew our diagram and said we start out at some angle and then we swing down, and we're going to say that the angle theta is just the angle from the vertical that the chain makes with respect to the chain on the swing with respect to the vertical. And we said our goal is to find acceleration at the bottom. We were assuming we knew the initial angle, the length of the chain, gravity. And last time we tried a really hard way and gave up, and then we had the easier way, and I'm putting easier in quotes because now we've got an even easier way. But the way we did it before is we said, well, the centripetal acceleration at the bottom is just v squared over r. We had the work energy theorem, we knew how to calculate work and kinetic energy, and we went through and did all of this stuff. But instead of doing that today, we're going to do something even easier. We're going to use conservation of energy. So our new basic equations are going to be, again, acceleration at the bottom is v squared over r. But then we're going to say k initial plus u initial equals kinetic energy final plus potential energy final. And kinetic energy is just 1/2 mv squared. And the potential energy due to gravity is just mgh. So for our symbolic solution, well, we have to choose where y is equal to 0, right, to plug in our potential energy due to gravity. And I think the problem works easiest if we let y equal 0 right at the pivot, so that our y is always going to be negative. Okay, so initially, when we start swinging, our kinetic energy is 0, and our potential energy is negative mgl cosine of theta naught, right? It's how far below y we are is going to be L times cosine of theta. When we get to the bottom, we will have kinetic energy, 1/2 mv final squared, and our potential energy will be negative mgl because y will be negative L. So there it is. That's the equation we have to solve to find the velocity at the bottom. It's pretty simple. Wait a minute. We didn't talk about tension. Is the tension force conservative? Well, just like we found before, tension is orthogonal to the displacement, so it doesn't do any work, so we don't need to worry about it when we're using work and energy and such, okay? So we can just ignore tension. Okay, so here's the equation we needed to solve for V final, and I'm going to bring the GL to the other side, multiply both sides by 2, and I'm going to factor out the GL, then multiply both sides by 2. And there's V final squared, but of course remember acceleration is V squared over L, so I just have to take that, divide by L, and I get 2G, 1 minus cosine theta naught. And as you recall, that is the same answer we got using the work energy theorem, but this was a heck of a lot easier. All right, plugging in numbers. Again, we can plug in numbers. Let's say that theta naught is 90 degrees. That means the acceleration, the centripetal acceleration is 2g, just like we found before. We can plug in numbers. The units work out just as they did before. Gauge and guesstimate, once again, that seems like a reasonable acceleration. And the limits work the same way they did when we looked at it before, that, playing with how we would expect things to change, our equation seems to be okay. All right, so that is the end of our example problems today, and it went a lot quicker than last time because conservation of energy is really, really nice.